In this video, we're going to show how to report measurements. When reporting measurements, units are almost always required. Just writing 10 as an observation doesn't mean anything. It could be 10 millimeters, 10 centimeters, 10 meters, or 10 kilometers. The units always have to be expressed, otherwise the measurement's pretty much meaningless. When writing a measurement, there should always be a space between the number and its unit. 10 space m, I know that means 10 meters, but 10 with no space m, 10m, could just mean 10 times the mass, because we use m for mass. So always try to put a space in between the measurement and its unit. But there's never a space between a unit and its prefix. For example, we never write 10m space m if we want to mean 10 millimeters, and we don't write 10 c space m for 10 centimeters, or 10 k space m for 10 kilometers. No space between a unit and its prefix. But there's always a space between each part of the compound unit. So for example, here we have 10 meters per second. So we know it's meters per second. Because if I write it like this, I might mean 10 millimeters per second, or do I mean 10 meters a second? You always have to put a space in between the parts of a compound unit like this. So when we look at a scientific report or a paper, or even a question in an exam, we should be able to tell how many significant figures each measurement has by looking at how it's written. All digits are significant except for zeros that are not measured, but are used only to position the decimal point. So here we've got a number. The zeros here aren't significant, only the 2 and the 5 are significant. We don't know anything about how accurate this number is to the next decimal place. It's only written to 2 significant figures, and this number is known to 2 significant figures. But this next one, we know that the 1 is significant, we know that the 5 has been measured, but we don't know anything beyond the 5. So all the way across, 1, 2, 3, 4, 5, 6, 7, all of those numbers are significant, and this one's known to 7 significant figures. And this last example, the NORD is only there to position the decimal place. So we've got 1, 2, 3, 4 significant figures. We need to take extra care when zeros end a number. Here we've got one from the previous slide. So we have the 2 significant figures of the 2 and the 5. But this next one looks the same, except it's got a 0 on the end. That 0 has been added because all 3 of these numbers are significant, including that 0. So it stretches all the way to knowledge in this last decimal place here. And this one's known to 3 significant figures. Similarly, the next one, I've got 2 zeros on the end, because whoever's measured this knows it accurately to that level, this number of decimal places. And this one's known to 4 significant figures. And the last example here, we've got accuracy known in the first and the last digit. So this goes all the way across and is known to 8 significant figures. So take care with zeros that end a number. Look, here we don't have any decimal points in our number. Only the 1 is significant. None of the zeros are. So this one's only known to 1 significant figure. But this next one, a decimal point's been added. And this tells me that all 3 of these numbers are significant. 100 dot might look a bit strange, but that's a number that's been written and known to 3 significant figures. So now let's think about when we have to combine measurements, when we have to multiply or divide them, or add or subtract them. But when we multiply or divide, the answer should have the same number of significant figures as the measurement that has the fewest. So let's look at a typical question. How many moles are there in 18 grams of water? The molar mass of water is 18.02 grams per mole. So the calculation we want to do is number of moles equals mass divided by molar mass. 18 grams divided by 18.02 grams per mole. We can type that number into our calculator, but what we've got to remember is the 18 is known to 2 significant figures, the 18.02 is known to 4 significant figures, so the one with the fewest is controlling how accurate the final answer should be. So the final answer, whatever the calculator says, has got to be written to 2 significant figures. It's 1.0. Remember that a 0 after a decimal point that's written is significant. So this answer is indeed written to 2 significant figures as required by the measurement with the fewest number of significant figures. It's a second example. So what's the mass of 2 moles of water? The molar mass of water is 18.02 grams per mole. So this time we want to do mass equals number of moles times the molar mass. 2 moles times 18.02 grams per mole. Type that into your calculator, you get 36.04. But we only know this number to 1 significant figure. We know this one to 4. This one is controlling how accurate our answer can be. It could only be written to one significant figure. So instead of 36.04, we've got to write that to one significant figure. We've got to round up, and the answer is 40 grams. 40, without a dot, one significant figure. See how it works. See how the number that we've got at the end can only be as accurate as the least accurately known answer that we've got. So the other case is when we're adding or subtracting. Now this is a bit more tricky. The answer should have the same number of decimal places as the measurement with the fewest number of decimal places. So what is the total volume if 1.52 litres of water are added to 0.3 litres of water? We can add that up and we'll get an answer. But let's look. 1.52 is written to 2 decimal places. 0.3 is 1 decimal place. So in the 0.3 we have no knowledge at all of what's going on in this next decimal place. So we have no knowledge at all in that decimal place in the answer. So the answer is only written to 1 decimal place. 1 decimal place is 1.8. 1 decimal place, but look, that's 2 significant figures because both the 1 and the 8 are significant here.